Welcome everybody to week 13, day 2. Today we are going to do more exciting, no wait, we're not doing exciting stuff today. We're doing boring stuff today. It's really important boring stuff though. So last time we gave you a complete accounting of pretty much all the major tasks you would want to do in either Quake C or Unreal Engine. Today we're going to talk more about math. Yes, math. And why is that important? Because math underlies all of 3D game development. Like, even if you're not making your own game engine, you still need to understand the math that's going on behind it, because that's the things that make sense. So, let me fire up OneNote, and we are going to be doing math today. Yay. So, linear algebra, last time we talked about how to add two vectors together. Do you guys remember that? So if you have an x, y, and z of 10, 20, 30, and you add to it 10, 10, 10, it would turn into 20, 30, 40, right? So if you say move it 10, 10, 10 in this direction, it'll go from 10, 20, 30 to 20, 30, 40. So adding vectors, subtracting vectors works the opposite, of course, as addition. Dot product tells you, are two things pointing in the same direction? Cross product tells you if something's to the left and the right. Okay, that's oh, my favorite. Yeah, it's actually really important though. And so yeah, dot product. I mean, like, if you want to do things in video games, like this whole semester I've been sort of going over all the different tools you have in your toolkit, and then you can assemble those tools to make your games or whatever you want. For example, if you want to look at my code for laser-guided rockets in Quake C. Let's see. Quake source custom. Come down into weapons.qc, and we are going to search for laser-guided. There we go. So there is a function called make rocket, and there's a bunch of different weapons that can all make a rocket projectile. And so what I did, I noticed that we had the same code copied and pasted over and over again. So what I did was I combined them into one function, and then you just pick out which one you're doing. Are we making a incendiary cannon, rocket launcher, that kind of stuff. And if it has lasers, it goes slower than a normal rocket. Let's see here. Faster rockets travel faster. And so you can see, oh, I don't know if we've done this, actually. If you multiply a vector times a scalar again is a fancy word for a number. What do you think this is doing here, that line of code? Velocity is equal to velocity times 1.2. If you just had to guess, what do you think that line of code is doing? Don't look at the comment 2 lines above it. It's math. It's linear algebra, but it's not hard. You know, it's applying acceleration. Yeah, it's increasing the velocity of the rocket. Yeah. By how much? 20% more velocity. Yeah. So let's do more linear algebra. So if you have a vector, like, let's say that it's traveling 100 miles per hour to the east, none up and none in and out, and you multiply this vector by 1.2, what happens is the velocity becomes 120, 0, 0. If the velocity was 10 east and 10 up and 10 in, and you multiply it by 1.2, it becomes 12, 12, 12. Okay, so however fast it's traveling east and west gets increased by 20%. However fast it's moving up and down gets increased by 20%. How fast it's moving in and out gets increased by 20%. You guys understand? So this is a vector times a scalar. You just increase all the elements of the vector by that amount. Make sense? A lot of this linear algebra stuff is just like common sense. You know, it's like, how much faster? Well, it's 1.2 times faster. Not too bad. But yeah, you might not know that what happens when you take a vector and multiply it by a scalar. Well, that's what happens. Each of the components, the x component, the y component, the z component, each of them get multiplied by 1.2. There you go. So here it is, what is my speed? Oh, that's the speed of the rocket. So the speed of the rocket is equal to 900. Yeah, it starts off, the velocity of the rocket starts off as a unit vector. So it starts off at a speed of 1, which is like 1 centimeter per second or something. Except they're not centimeters. I don't actually know what the units are. But it's like 1 centimeter per second. So it's very, very slow by default. And so what happens is we take that but it's pointing the right direction. That's why we start with it. So we start with it, whatever direction we're looking in, that's the direction it's moving with a magnitude of 1. So whatever direction we're looking, the rocket would come out traveling at a speed of 1 centimeter per second. We accelerate it based on mass speed. So, not a cluster rocket, there. So that's a regular rocket there. So it now has a speed of 900 for a regular rocket. So it's traveling 900 centimeters a second or whatever, except it's not centimeters. And then if we bought the upgrade to have faster rockets, it is then traveling at a speed of 900 times 1.2, so 1080, right? Vector to angles converts the direction it's going into a rotation. So in order to rotate the rocket to point in the direction it's shooting, because if you don't do that, the rocket will come out sideways like this. And that's a bug I've had before. You know, you shoot something. It's the reason why we use the confetti balls. They're balls. It doesn't matter which orientation they come out. But yeah, I would shoot a rocket and they'd always be pointed, you know, in the x direction. So if I shoot it facing the x direction, the rocket comes out pointing the right way. If I shoot down the y, it comes out sideways, which looks terrible. And so this function here, vector to angles, you give it a direction the thing's moving, and it gives you a rotation, basically, that will make it point in the direction that it's moving. So, linear algebra. And yeah, it's a bit weird. And then it is given an angular velocity, which is how fast it's spinning. If you use the Daedalus rocket cannon, it actually generates a rocket that kind of tumbles end over end like this. Why? I don't know. It kind of looks cool. I don't know what to tell you. Actually, it's a sprite, so I don't even know what's going on there. It's just a sprite is a 2D image, so you can actually set the model of something to be a 2D image. And so it's just a 2D image that flies away from you. It looks like a little explosion traveling away from you. I think originally it was a model of something that actually looked like this pin, and so it would fly out and kind of do this kind of spinny business. Looked kind of cool. I don't know. Okay, so laser sight. So if we have the laser sight upgrade, then it will set the think on the rocket to be rocket track dot. If we don't, the rocket's think just takes place in 5 seconds, and it thinks to remove itself. So if you shoot a rocket launcher normally, if it travels for 5 seconds without hitting anything, it's probably not going to hit anything, and it erases itself so it doesn't fill up the array of all the different entities in the world. But if you want it to think, so if you want the rocket, every 0.1 times 4, 1 times, so every 0.1 to 0.5 seconds, something like that. So I don't have all the rockets think at the same time to cut down on network lag. Basically, every 0.1 to 0.4 seconds or so, 0.5 seconds, the rocket will wake up. And what will it do? That's its next think. That's the time it's going to think next. It's going to be a brief second from now, half second from now or so. What it's going to do, it's going to call that function. So let's find rocket track dot and just look for the equal sign. That's where it is. It's kind of nice. And the file saved. Did I change anything? So for rocket track dot, it wakes up, and I am the rocket now. So when you see self, that is me, the rocket. Because when the think function gets called, it sets self is just a global, and so every tick, every frame, the server checks to see if any of the objects in the world had their think come up, and if it did, it calls them one at a time, and it sets self to be equal to whatever number is whose time is up. That's it, and then it calls whatever think function they have, and so it sets self to be the rocket. And then rocket track dot gets called. Self is me. I'm the rocket now. I added in a thing so the rockets will go away if too much time has elapsed. Because with a laser guided rocket, you can actually sit there and spin them in place forever, right? And just create this like vortex of missiles, which while cool, will end up lagging out the server if you have too many of them. So if the rockets don't hit anything within whatever this value is, I don't remember what I set it to, then it removes itself. So, and it's a timer. So remember how we talked about timers? So basically, in Quake C, you set a think function, and in 0.1 to 0.4 seconds, this function gets called. Well, guess what? We're doing it again. So technically, I didn't have to set that again, but it would sit there and re-up. It's hit snooze essentially, and it comes up again and again. Every 0.1 to 0.4 seconds, the thing comes up and thinks again, over and over again, until it exceeds this time. Okay, so we call the find function, which I don't think we talked about actually. That might be good to add to our list. So it finds everything in the world that is a timer, and it checks to see if that timer is owned by the player that shot me, and if its think function is sniper sight update 2. So that's the laser dot. When you hold down the sniper button, it creates a dot in the world whose think function is sniper sight update 2. And so basically what we're doing is we're searching through the whole world trying to find where the laser dot is. And then if we found one, if it didn't find one, if we didn't find one, it returns world. This function returns world. It didn't find it. If we did find one, then we're going to follow it. So we have no laser dot. Let's look for none of that. None of that. Right. Site equals TG. Site not equals world. Say position. Okay, so that is the... Okay, so basically if we find the laser dot, it writes down this vector is a vector temp. It just writes down the location that the dot's at. That's all it does. And then all this heat-seeking code we can skip because we're not doing that right now. If the person let goes of the laser dot, then it will use the last place that the laser dot was found, and so it'll just keep flying towards that point. So here we got. Now let's do some vector math. Okay. Is this C or is this Quake C, which is essentially the same? It is Quake C. It's not exactly the same thing as C. Most notably, you can do something like this in Quake C. You can't do it in C. So that's a vector and that's a vector. So this is doing vector subtraction. So what we have, let me sketch this out, this line of code right here. What we have here is we've got some point in the world, let's say the laser dot, let's make it red. is over here. And we've got the rocket, which is over here. And that's the point the rocket's at. So the user, it had been over here, and in the meantime, the user had like moved the laser dot this way. So we've got this thing called vtemp, which is the location of the dot. Let's say this is at, I don't know, 30, 0, 0. And our location up here, self.origin, is at 10, 10, 0. So the laser dot is here now. Okay. You understand? That's the vtemp x, vtemp y, vtemp c. And so in Quake C, you can actually subtract vectors. And in C, those would be 3 different variables, or if it was a struct, you would write a function or something to do it. But it's built into Quake C because linear algebra is so important in games, they actually just built in linear algebra into it. So it's actually a little bit easier to write code in Quake C for doing game development. But learning C wouldn't really help in learning Quake C. I mean, it's essentially the same language. There's just a few differences like this that just kind of make life a little bit easier for you. So what it's doing is saying take vector temp and subtract vector origin. This is a displacement vector. So it is saying v temp minus self.origin. And do you guys remember how to do vector subtraction? So what a displacement vector is, it's trying to create a vector from the rocket towards vector temp. And we use displacement vectors for 2 things. 1, how far away are we from the laser dot? 2, what direction is the laser dot? Okay, and so in order to do this math, it's going to be 30, 0, 0, minus 10, minus 10, 10, 0. And so it is 20 to the right, it is 10 down, and 0 in. You guys see that? It's 20 to the right, it's 10 down. And I'm not doing anything in or out of the z-plane just because I am not that good at drawing. Right? That makes sense? And so this thing is like 20 this way, and it's like 10 down this way, right? Kind of eyeballing it a little bit. You guys see that? It's 20 to the right, 10 down-ish. I don't know. Okay. So that is what the vector subtraction there is doing. It's creating this displacement vector, which is the distance from one point to another. And you take the point you're moving to the target minus your current point, usually. Then we normalize it. So when you normalize a vector, you turn it into a unit vector, pointing in the same direction. So we're going to turn it into a unit vector pointing this way, of length 1. And so we do that by getting the vector length. Let's see. So what is the length of a vector? Actually, it's pretty obvious, huh? The length of this vector it's the hypotenuse, right? So if we think about this in terms of like a right triangle, it's 10 down, 20 east. What is the size of the hypotenuse here? Anyone remember algebra? How do you compute the length of the hypotenuse given the length of the legs? Hazelton, you remember? Yes, it is the Pythagorean theorem. So it is the square root, if you guys remember Algebra 1 from back in the day, it's the square root of a squared plus b squared. So a squared, b squared, or vice versa, doesn't matter. So I just punch this into the calculator. 400 plus 100 square rooted is 22.3. So this guy is 22.3 units away. And we can use the Pythagorean theorem for that. That's vector length. And when you normalize, what you do is you do a vector division. So you take a vector, in this case 20, negative 10, 0, and you divide it by 22.3. So it works exactly the same way as multiplication. You just divide each component. You guys see that? So it's like multiplying by 1 over 22.3. And so each one of these components is going to shrink by a factor of 22.3. So 20 divided by 22.3 turns into 0.89. Uh, 10 divided by 22.3 is going to be a little less than a half. 0.44, negative 0.44, and 0 divided by anything is still 0. Okay, you guys see that? So now we've got a vector that is 0.89, negative 0.44. The length of this vector is 1. And we use normalized vectors all the time. And so it's so common, in fact, that there is a function for it called normalize. So you don't have to do the, computing the vector length and doing the division. There's just called normalize. You pass it a vector, and it normalizes it. And so this here is a vector just holding the direction, essentially, towards the target. So what we have now is that. Just draw it with a little bit more precision. So we have a vector of length 1. It's a vector of length 1. And it's pointing in the direction towards the target. And the reason why we do this is because we can now scale it based on our velocity. So dir is the direction we're pointing. This is going to be the, it's going to rotate the rocket to face in the direction that it should be going. So the laser dot's over there. It rotates to face it. And then we okay, we don't quite rotate yet. That comes later, but that's the direction we want to be looking. And so what we do now is we get the right vector and the direction we're looking, and we're doing a cross product with them. And so we have the cross product of the right vector of this guy and the cross product of our forward vector here, and we do some vector math, and if the result is less than 0, it's behind us. So cross product of this and this can basically tell us if this thing is back this way or ahead of us. So it's the reason why it's right and forward is because the cross product and the dot product, which you would think we'd be using, are just a 90-degree rotation from each other. So by cross producting the right component of one vector and the forward component of the other, we end up getting basically a dot product out of it. And so this is basically saying if the dot product is less than 0, return. So if we ever lose our lock-on, so like basically as the user is moving the laser dot around and the rocket's flying towards it, if you ever snap the laser pointer back this way, it's a little weird for the rocket to just flip backwards in place. It's also too good, right? Because like your rocket misses somebody, you can immediately spin it around and hit them from behind. And that's too good, right? Like once you've dodged a rocket, it's really lame for the rocket to then hit you from behind. And so this was a addition I made 14 years ago that basically will break the lock on if the dot's ever behind the rocket. Then it will rotate towards the target, and this function here will allow it to rotate at a certain speed, so it doesn't just have infinite rotational speed. Like it actually has a variable here called rocket rotate that holds the fastest it can turn in midair. And that's, again, a gameplay thing, so that you can't have these super agile rockets. If you move the laser pointer this way, the rockets will kind of curve towards it. And it's a cool looking effect, too, to have the rocket sort of slowly curve. And it keeps it from being too good, because otherwise you just keep the dot on somebody and the rockets would always hit them. Okay, so then now that we've rotated towards the target, we get our forward vector, we normalize it again. This is the direction that we're looking now. We set the velocity equal to the direction times 900. All right. So our speed is now 900 in the new direction. And that doesn't matter. And then we point ourselves in that direction. So once we have our velocity set, we call vector to angles, and then the rotate. Then it draws the thing rotating that way. So this whole nonsense here sans the cluster rocket code, or the heat-seeking code rather. I wrote that all in one go, and it worked right the first time. And that was quite honestly one of the biggest surprises of my life. The fact that all this vector math and everything, like I sat down with a piece of paper and I like worked it out. I'm like, all right, this is how this will work, and the thing and this thing and the normalization, and I sat down on a piece of paper and I worked it all out, and then I coded it. Probably I just coded it for regular rockets first, because all these details here with like the different types of rockets and things like that, none of that matters. Heat seeking wasn't in, I think, at that point. But just the ability to track a laser dot, which is, it's vector math. A little bit of cross-producting, a little bit of displacement vectors, with a heat-seeking code, you can see it's doing a vector length to see how far away they are, and does a dot product. There's a dot product, yeah. If you just multiply two vectors and Quake C, it does a dot product. I don't know why I didn't do a dot product down here. There's probably some reason for it. I just don't know what. It's always impressive to see code come together to make something unique. Yeah, it was really the high point of my programming career, because like when it worked, I was just like, what? I'm holding down the button and the thing's just chasing after it, and I'm just like, what? How did that happen? It's like I will never accomplish something like this again. It's just too good. So quite proud of that one. And then the other things were added in later: cluster rockets, support for the different rocket types, things like that. But faster rockets. But that basic linear algebra is that's why I'm saying it's so important for you to understand the linear algebra, to because it enables you to do things like this. If you don't know it, it's just like, I don't know, go into Stack Overflow, find somebody who said something similar and copy and paste it and hope it works. Like you got to have kind of the basic theory down. Okay. So today, so far, we've talked about vector times scalar, and now we're going to be talking about matrices. Matrix math, which is a big topic. So the way that it works in 3D video games is that when you code it without actually checking to see if it would work, and I just wrote the whole thing because I couldn't. It was one of those things like if you don't have it update the rotation and stuff like that, then it doesn't. You can't really do anything with it, right? It's just a regular rocket. And so I just kind of coded the whole thing, and then you can see I still have those print statements in there. this kind of stuff. So I've got these different print statements that were used in debugging and things like that, and I basically didn't need them because it just worked right. But you know, I tried different values for, like, you know, how narrow a cone it'll lock onto things. This is for heat seeking, things like that. So printfs and yep, all that stuff's in there, but it turned out not to be needed. But yeah, I print things by default anyway. All right, so let's talk about matrix math. So specifically, a matrix times a vector. So let's say that we're at point 10, 0, 0. So you'll typically have your point held in a 4x1 vector. So this corresponds to x. All right, that's your x value. I shouldn't use x here. Maybe, I don't know. This is your y value. This is your z value. Okay. So in 3D games, your point, you know, let's say you've got a screen, you know, and, I don't know, x, y, z. So you've got some point in space like this, and that could be like the origin of your rocket or something like that. And there's a couple different operations you can do on it. And these are the same operations you do in Unreal Engine. You can translate it, which means you can move it this way, or move it this way, or move it into the screen. You can translate it, you can rotate it, and you can scale it. So rotation means you rotate it around, it rotates around the origin, right? So it rotates around whatever you have set as the origin. And scaling it means, you know, doubling its distance or whatever, you know, from the origin. All three of these things can be done in a matrix. And so a matrix is typically a 4x4 matrix, and it embeds inside of, I'm about to draw the numbers in here, but it embeds translation, rotation, and scaling all in one go. So you actually don't have to do multiple steps of math to do translation and rotation and scaling. It's all held in a single matrix. It's called a transformation matrix. And then this is like a position vector. So the first value in the position vector here is your x location, your y location, your z location, and the fourth one is just always 1. And that's because it's going to make this thing work, and you'll see why in a second. So 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. This is a transformation matrix that does absolutely nothing. This is called the identity matrix. It's like multiplying by 1 or adding 0. If you do the matrix times vector operation, which I'll show you how it works in a second, if you do this, you will end up with 10, 0, 0, 1 again. So you go to all the trouble of all the arithmetic I'm about to show you, and the result you're going to get from this, as a spoiler, is going to be 10. It's a horrible 1 there. It's going to be 10, 0, 0, 1. So this time this is going to be this. Why? This is identity in transformation matrices. Okay. So how do we do it? How do we multiply a matrix and a vector like this? Well, what you do is you take this vector here and you turn it sideways, and I'm just going to write it kind of above here, 10, 0, 0, 1. And you multiply 10 times 1, 10 times 0, 10 times 0, 10 times 0. These are multiplies. 0 times 0, 0 times 1, 0 times 0, 0 times 0, 0 times 1, 0 times 0, 1 times 0, 1 times 0, 1 times 0, 1 times 1. And so it's going to look I'll just draw it over here, I guess. Are you doing the thing again? You're doing the bug? Doing the bug? You're doing the bug? Cool. Relaunch. So what you do is you multiply down, and then you're going to add across. That's how you do matrix times vector, and I'll show you what this means. So you turn the vector sideways like this, you multiply down, and you end up getting 10 and all zeros, and 1 0 0 1. 10 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 1. Can you show us how to use a calculator? No, there's no calculator that does this. You have to do it by hand. So there's probably website calculators that'll do this, but you need to understand the process to understand how this works. So I'm not done explaining it yet. So you take this, you turn it sideways, and you multiply 10 times this one, this one, this one, this one. 0 times this. Do you see that? So 10 times 1 is 10. 10 times 0 is 0. 10 times 0 is 0. 10 times 0 is 0. These two columns turn into zeros, and 1 times 0 is 0. 1 times 0 is 0. And so it ends up being this. So that's the first step, multiply down. You take this vector, you turn it sideways, and you multiply this number times the first column, this number times the second column, third column, and fourth column. You multiply them down, and then you add across. Is matrix math binary? No. No, it's not binary. Maybe I shouldn't have used 10. And you add them across, and you get this 10 0 0 1. Grab my face. And so that is the same as before. So you multiply down, you add them across, you end up getting the same result, because what we had there was the identity matrix. So let's make it a little more interesting, because that was almost too easy. It doesn't really teach you anything. Okay, fine. Let's use not binary looking numbers, I guess. Let's do a more realistic example. Dang it. Okay, so for this one, we're going to have our x location be 10, our y location be 20, our z location be 30. And now I'm going to explain what a little bit of the matrix means. This part right here is the translation section. So this number here means how far it moves x direction, how far it moves in the y direction, and how far it moves in the z direction. That's how far it moves in the x direction, that's how far it moves in the y direction, and that's how far it moves in the z direction. So the different parts of the transformation matrix correspond to different operations. And like I said, it does all of them at the same time. This area here corresponds to rotation and scaling. So rotation, so scaling is this. That's the scale of it. This is a scaling of 1. That's why it doesn't do anything. So scaling is that part. And then rotation is this 3 by 3 area here. And I'll explain what that means more in a bit. But this is almost always going to be 0. Let me make that a 0, not a 6. This this are almost always 0. They are used just infrequently. And this is always going to be a 1. That's always going to be a 1. And, you know, when I say always, there's always weird edge cases where, you know, people don't use 1, but there's like weird skewing and things like that, operations you can do. But we'll ignore those for now. We're just going to focus on translation, rotation, and scaling. So this 3x3 area over here means don't rotate it and keep it at a scale of 1. Okay, cool. Now for the translation part, I'm going to put in some numbers here. How far do you guys want it to move in the x, y, and z directions? Just give me some numbers and I'll fill in the gaps here. $69 in the x direction. All right. 30 in the y direction. Maybe I'll use a thinner pen. So it's going to move 69 in the x direction, 30 in the y direction, and 92 in the z direction. Okay. It's not really readable. Okay, so let's do the multiply down and add across. So we take 10, 20, and 30. Let's see, maybe we can zoom out a little bit here. And we're going to take 10, 20, and 30. We're going to just sort of hypothetically, you know, we're not, you know, not moving these, but, you know, you just kind of write them up there. So we take the numbers, kind of write them up there to help you with the calculations. And then you're going to multiply, you're going to do a vector multiply, vector times scalar multiply. Right, so this 1, 0, 0, 0 turns into 10, 0, 0, 0. Does that make sense? So in the output matrix, you're going to get 10, 0, 0, 0. You guys see that? So 10 times this column. So that column is going to get multiplied by 10. 10 times that whole thing. Okay. And then for this column, you're going to multiply this column by 20. And so what do you get? 0, what? What do you get? So this column gets multiplied by 20. 0, 20, 0, 0. This column gets multiplied by 30. What do you get? 0, 0, 30, 0. Mm-hmm. Good. And then for this one, we're going to multiply 69, 30, 92, 1 times 1. So I hope Hazelton, Torres, and Wong are doing it. Hopefully all of you can tell me what this area here times 1. Hopefully you guys can multiply by 1. What do we got? I want to see everybody type it out, not just the 3 students. What is 1 times this column? That was hard. You wish you had your calculator. Yeah, fair enough. Diaz, do you understand what's going on here? Good. All right, so the answer is going to be, let me scroll over to the right a little bit. $69, 30, 92, and 1. Okay. So we multiply down. So that's step 1, multiply down. So you just take the thing, turn it sideways, and then you do a vector times column multiplication, and then you add across. And so we add across. It's 10 plus 0 plus 0. And do you see where the translation by 69 is coming? So 10 was our original position, and it's moving right. Hazelton is a true math prodigy. He is. He is. Okay. All right. So what do we got? What's our final answer? 10 times 69. 10 plus 69 is what? 79. 20 plus 30. And yeah, don't feel bad about reading my handwriting. Like, in discrete math, I flubbed a proof because I misread my handwriting. It's like, is that a 2 or a 7 or, I don't know. Is that a 9? I don't know. Alright, so 122, very good. And of course, the bottom number is 1. And so you see what we did here? So we had a point, and we wanted to move the point 69 east, 30 north, and 92 in. And that's what we got. 69 east, 10 plus 69 is 79, 20 plus 30 is 50, 30 plus 92 is 122. Now you might be like, well, why do we need this whole matrix thing? You know, we could have just added this column and this column, and that's true. That's true, because this is an identity matrix. This whole thing here does nothing. But the reason why we're going through this is to show you that this part here corresponds to translation. Now, if we start messing with this, then you know, in one matrix operation, you can do rotation and scaling and translation all at the same time. So, so rather than having to repeat this process 3 times and do a translation and then do a rotation and scaling, you can do it all at once. And computer CPUs are optimized for 4x4 matrix multiplies. If you go back to my college days, nope. Yep. Modern Muscle Extreme. We only sell the Hemi performance parts you need to take your hot rod to the next level of competition with forged internals like pistons. No, that's actually not it. There we go. 97. Yeah, back when I was a junior in college. And what it was an attempt for Intel to kind of cash in on the 3D video gaming craze, right? So 3D graphics exploded on the scene with Quake in 96, really. Yeah, 96 was Quake. And so a year later, Intel comes out with a chip that supports matrix multiplies in the CPU. Okay. And so it drastically accelerated how quickly an Intel chip would be able to do this. Okay. And they had all sorts of advertisements, and nobody understood anything about what it meant. Like, they had people, I don't know, dancing around in, like, bunny suits. If you guys know what those are, like the clean room. Full body suits. Yeah, commercial. Yeah, let's see this. Yeah. It's a.
Here, in the world's most advanced manufacturing environment, Intel technicians are making Pentium processors. Nearby, other Intel technicians are adding something new.
Can mute it for the copyright strike. Yeah, so it showed like all these people like dancing around in like the bunny suits and things like that. And you'll call it fun. And nobody had any idea like what any of that meant. You know what I mean? Like, okay, there's people dancing. I don't know. So that approach, though, is still being done today. For example, my i9-7900X has what's called AVX 512 in it, which is the latest version of the thing that started 24 years ago with MMX. And so what it does is it allows you to do basically a row of multiply and adds in a single operation. So rather than having to do all those multiplies and all those adds, it can do one one operation, and it will do an entire row, basically. And so it greatly accelerates. It's like 4 to 16 times faster, I think, something like that, in terms of like doing specifically this operation. Why 4? Because the 3D graphics have a 4x4 matrix, and so the design of the CPU followed the math that you're learning today. So you're going to take that piston cup. It's funny. Okay, so let's do scaling next. So let's keep our translation in here, and let's scale it by a factor of 2. And this is uniform scaling, so it's going to scale in the x direction, the y direction, and the z direction by 2. So it's a doubling. Okay. So now let's repeat the process. Now we're going to do translation and scaling all at the same time. All right, Hazelton, you're up first. Multiply 10 times this column here. What do you got? 10 times 2, 0, 0, 0. 20, 0, 0. Yep. 20, 0, 0, 0. Okay. And then Torres, multiply 20 times 0, 2, 0, 0. Spraggins, get ready. You'll do the next one. 30 times this. All right, so Torres, what do you got for the second column? Yep. 0, 40, 0, 0. You guys see how this is scaling? We were at 1020, now we're at 2040. And then we're about to add this. Okay. So Spraggins, you're up. Spraggins? What is it? You tell me. What is 30 times this column here? 30 times 0 is 0. 30 times 0 is 0. 30 times 2, this column right here, the third column. 30 times 2 is what? 60 and 0. Good. Okay. And then I will do the multiplication by 1. I'll just give this one to you guys. The math is too hard for you to do, I'm sure. 69, 30, 92, and 1. Okay, then we add across. What do you got? So you see what happened here? The 10, 20, 30 turned into 20, 40, 60. So turn it sideways. So this is scaling in the x, scaling in the y, scaling in the z. But usually we do uniform scaling. Not always. It's pretty common. So 89, 71, 52, and 1. Yep. That's exactly right. Made it a little bigger. It should be a little easier to read. And 1. So you guys see how that happened? It doubled the x, y, and z values, and then it added the translation component to it. Pretty straightforward, I think. And we'll do one more, this time with rotation. This kind of math is fun. Yeah, I know. It's like linear algebra is considered the last math class you have to take. You take it after differential equations. Hazelton right now is taking differential equations and loving it. He thinks it is the absolute best class of all times. I'm a little jealous because he says how much more he loves it than my classes. But yeah, but linear algebra is usually taken after differential equations, and so people think that it's harder than differential equations. you know. It's not. It's just, if you know how to add and multiply, like, maybe even subtract and divide, then you can do it. Okay. Differential equations, stupid long. One problem took me 1 hour. Yeah. Yeah, I wrote programs to solve my differential equations for me. All right. So let's do rotation now. So scaling is this bit here, and then rotation is going to be the kind of thing where you look up the equation for it. Transformation, matrix, rotation. And you look up a cheat sheet for it. Okay. This is 2D. So you see translate X, translate Y, that's the rotation part. Rotate around X, rotate around Y, rotate around Z. So this would be a rotation around the Z-axis here, right? You can think of the Z-axis as coming out of the screen. So I think we'll do that one. It's easier to draw. So the rotation around Z. So yeah, it's just the 2D rotation then. See that? That's the 2D rotation. Cosine, cosine, sine, negative sine. Cosine, cosine, sine, negative sine. Yeah. So that's what you're doing when you do a rotation in 2D. You're rotating around the Z-axis, even though there is no Z-axis in the 2D space. So we'll do that one. We'll do this one. Okay. And so yeah, you just have a cheat sheet, you know. I could probably memorize it if I wanted to, but right. And so what it's going to do, it's going to rotate it clockwise around the origin, around the Z-axis. Yeah, cool cheat sheet here. There you go. You guys see that? It's basically what I have been lecturing on today, right? So this chunk of the matrix corresponds to translation. The thing here is the scaling in the X, Y, and Z. And then the rotation, it depends on which axis you're going to be rotating it around. We'll do it around the Z-axis. Okay. I don't know how this is helpful, but I'll copy this onto Discord for you. There you go. Okay, so let me set the scaling back to 1 just to keep things simple here. So 1, 1, 1. Okay. And now we are going to do a rotation. So let's do a 90 degree rotation. So we're going to rotate it counterclockwise 90 degrees. So what is the cosine of 90 degrees and what is the sine of 90 degrees? You guys remember? A little trig now. A little more advanced, but you know, if you're gonna, yeah, 0 and 1, right? So the cheat sheet, which I have up on there, okay. So the cosine of 90 is 0. The cosine of 90 is 0. The sine of 90 is 1. The negative sine of 90 is negative 1. So there you go. Is this right? No, this is a clockwise. It's a clockwise rotation. Sorry. It's not counterclockwise. Okay. So, let's do the math. Right? Is this clockwise or counterclockwise? Negative 20. 10. Let's see here. 10 is going to come in here. So it's going to be 10 in the extra. So it's going to be, we're going to start off at 10 20 up here, and it's going to turn into 10 in the y direction and negative 20 over here. So it's going to be a counterclockwise rotation. Okay. Okay, so Torres is doing the math again. 0, 10, 0, 0, negative 20, 0, 0, 0. Third one's the same, so I don't even have to erase that one. And the last column is the same also. So it's going to be very similar, except no scaling on it. Actually, I could just leave those pluses in there, can't I? So we got 0, 10. I'll just erase them all. 0, 10, 0, 0. Neg 20. Is that neg 20? Yeah, neg 20. 0, 0, 0. 0, 0, 30, 0. We add them together. Now, if we weren't doing any translation, you'll see the result we're going to get is negative 20, 10, 30, 0. So if this was the input, 10 east, 20 up, here, around the origin, this is rotating to be negative 20, so this rotates this way. Let me get rid of the text underneath there. So if we were at 10, 20, this turns into negative 20, 10. So back this way and up a little bit here. And so this is a negative 90-degree rotation around the origin. Okay. And then after that we do the translation. So it translates this way after the rotation. Yeah, so the answer is 49, 40, 92. Sorry, 49, 40, 112, 1. Yeah. 122, 1. Okay. You guys got it? So by using one of these 4x4 matrices, you can translate, you can rotate, you can scale, and there's that cheat sheet that just kind of shows you how to do it. And you can also just look at oftentimes you can look at a transformation matrix like this and just be like, all right, I see what it's doing. This part here is the translation, and then I see they're doing a little rotation here. No scaling; it's all ones, you know. And that's what your quiz for today is going to be. It's just going to be looking at maybe doing one of these multiplies, and then looking at this thing and just figuring out the translation part, the rotation part, and the scaling part. Okay. Sorry, yeah, that was my bad. You guys got it right. You guys got it right. This is not the identity matrix anymore. Welcome to the Matrix with Keanu Reeves. Okay. So, yeah, that's basically all the linear algebra you need to know. There's also matrix times matrix, which is used if you want to composite multiple transformations on top of each other. For example, if you have one transformation matrix for your shoulder, and then you have a transformation matrix showing how you get from your shoulder to your elbow, and then one showing from how you get from your elbow to your wrist, and one showing how you get from your wrist to your lower joint, to your middle joint, to your outer joint. That's how you can compute the position of your fingers. It's actually a matrix multiply of the transformation of each joint, each child. Spine, shoulder, elbow, wrist, finger joint, finger joint, finger joint, and then that'll compute and then there's probably a little offset in there for the length of the bone. And that'll tell you where, given a set of, transformation matrices showing how much this is rotated. It's rotated 90 degrees, rotated 0 degrees, right? You do matrix multiplies to composite transformation matrices on top of each other, and then you can push a mesh out corresponding to the little tip of your finger, and it will draw in the right place. So that's matrix times matrix. I don't know if we're going to go into it because usually your game engine's just going to handle that for you. Kind of conceptually, that's why we would do a matrix times a matrix. Is you never kind of need more than one 4x4. You know what I mean? Like, you know, once you've multiplied all these matrices together, you can render this mesh just using whatever that final product was of all the matrices being multiplied by each other on top of each other. And then you rewind back up and do another multiply, and that's how you draw skeletal meshes. It's a series of matrix multiplies, drawing the bone and then going down a level and doing another multiply and drawing the bone and drawing, you know, so each joint is going to end up in a matrix multiply. Like a skeletal body matrix math, yeah. Mm-hmm. And so anytime you see a skeletal body and they're animating and stuff, all of those joints have angles on them. And so that is a rotation. The joint angle is held here. A scaling usually is not going to take place. Scaling is fairly unusual. Maybe if you're like Miss Incredible or something, but usually it's just a rotation and a translation. And that shows like the bone, the length of the bone is the translation, and then the rotation is the joint angle. And so you just matrix multiply, and that's where the wrist draws. And then you multiply the wrist angle times the length of the bone of your hand, and that's where the knuckles are going to appear, you know? So that's it. That's what's happening. I'm not going to do that. But in order to do a matrix multiplying, just in case you're curious, you pull out one column of the matrix and multiply it, and put it back into its spot. And then you take the second column and do this and put it back into its spot. It's this just 4 times. You do this operation right here on each of the 4 columns of the matrix that's multiplying it. That's it. We're not going to do it. At that point, you usually just want the game engine to handle it for you. Yeah, but it's underneath every video game, you're going to find math, and people that don't know how to do math end up writing really, really bad programs. Like I don't know if you guys have heard of Yandere Simulator. So they're famous for writing clunky and horrible code. So yeah. Infamously bad code. Yeah. That is some top-notch coding right there. If this .yandere personality type is graceful and you are in the gardening club, if you're haughty and you're in the bullying club, if you're lively and your persona type is also social butterfly, then you gain a chameleon bonus. If only there was a better way of writing this. Ah, Lord, this is so good. I'm gonna save this one. This is going on the memes channel. Yeah. Yeah. So anyhow, the point is like if you don't really understand like the underlying basis for this kind of stuff, you just kind of end up writing, you know, just really kind of gnarly stuff. And you don't really have to have it super massive. This kind of stuff, yeah, like vector stuff, like understanding that if you had a normalized, get a direction, vector length to get the distance, multiply to scale up or scale down, things like that. This is your like bread and butter. This kind of stuff with the transformation matrix, it's usually you're not doing this by hand because it's a lot of work to do by hand. You're not doing like you'll see me draw nodes for like this kind of stuff. Like I'm going to do vector length, you know. For this kind of stuff, there's usually some sort of node that does that for you, like rotate. You know, use a rotator or something. Rotate something around an axis. You know, rotate something 90 degrees around the z-axis. Like there's going to be a node in there for you. You're not going to have to do this by hand. Or even, you know, like this where, you know, you do vector length by connecting up nodes. You're not going to be getting down to the nitty-gritty level, but you kind of have to understand what's going on when you do a rotate, translate, that kind of stuff. Okay. Did I post that twice on memes? There we go. Okay, 4 minutes left. Let me just pull up Unreal Engine to show what I'm talking about. Quake C, of course, has functions like this, where given a vector, it generates a rotation. Right. So behind the scenes, there's going to be a transformation matrix. That's basically holding the rotation around x-axis, rotation around y-axis, rotation around z-axis. So that's kind of the level that you work at. You know, you don't see me. There's no 4x4 matrix directly. Do you get what I'm getting at here? Like vectors, we work with directly. You know, take the velocity and scale it up by 20%. You know, but matrices, it's usually a little bit more indirect. Like I'm going to just set the angles, which is the rotation around x, the rotation around y, the rotation around z, and then the engine handles it. You guys kind of get what I'm getting at here? It does help to understand. Yeah, absolutely. Absolutely. So let me just show you what this would look like in Unreal Engine. I'm still confused what that dot there means. An update is available. Is it though? There's not. There's no update. I don't... 41 gigs. And these things don't show you the size of them either. Like, how big are they? I don't know. I actually mailed the Epic people. I'm like, hey, you know, it'd be cool if, like, when I go to buy something on the marketplace, if it had a size on it. You know, like, I would kind of, because, like, they're not small. You know, like they're like I've literally spent a lot of money on my computer just for hard drive space because this kind of stuff takes up so much room, you know. And they're like, yeah, that's a request. They wrote back. They're like, that's a request we get a lot. Well, we'll look into it, you know, because it's like here's the modular industrial area. All right, cool. How big is it? Yeah. It's so frustrating. How, like, before I download this, could you just like tell me, like, is this 100 gigs? Because like my stupid little game was 140 gigs by the time I finished it, and that's like the size. That's like bigger than Red Dead Redemption or something, you know. And it was just from importing, you know, assets, and I was like, that's not free, you know. I mean. If all you have is like a 1 terabyte SSD, that fills up your SSD real fast, trust me. And then I was pushing all this stuff out to Perforce. We were using a server that would synchronize people's files across the things. And it took so long, I ended up spending most of my time on the project just uploading assets because they were so big. It spent like 8 hours uploading, you know. And the people that were working with me were supposed to download 140 gigs on Oakhurst internet, you know, like... Yeah, forget about it. So, it's just one of those things. And so what you can do is you can hit add to project, and let's add it to fall 2021. Watch this. Watch. If you hit add to project, then it tells you it's 2 gigs. Cancel. That's how you find out the size. You buy it, you add it, and you cancel it real fast. And then now you know that that's a 2 gig download. Okay. And I'm like, why the hell? Why is this the way that? Why? How is this my life? You know? Okay. So let's see if we can find some examples here. Who are you? Confetti ball, main character, play sound 2D, spawn actor. Yeah. Okay. So when you spawn an actor, there's this thing called a transform. Okay. And so what's a transform? Guess what we talked about today. All right. So if we split this transform open, which we can't because it's currently connected. Let's break the connection. If I can click on the thing. Come on. There we go. So if we split it, you can see that a transform, which is what we talked about today, 4x4 matrix, they don't show you a 4x4 matrix. They break it into the 3 things we talked about today. The transform component, the rotation component, and the scaling component. And it does behind the scenes, it puts together the 4x4 matrix for you behind the scenes. And if we can split this one out, so you can get the transform. This is the 4x4 matrix for an object, and you can split it, and then you can just grab the location out of it. You can grab just the rotation out of it. You can grab just the scaling out of it if you want. I don't need to do that, and so having it not split makes more sense. But if you wanted to, you could like split out all the stuff, keep the rotation, but reset the scaling back to 1 or whatever. Like you can play with the individual components if you want to. It's very common to do what I just did, splitting it up and taking the rotation and splitting that up and setting the like the yaw to a certain value, or not having any pitch. A lot of times you want the things to be always horizontal, like parallel to the ground. Like you oftentimes don't want your goblins in the world to be tilted forward because it looks really weird. So it's very common to like split all that stuff up and just set the rotation about, the pitch to 0 and zeroing it out so everything is like upright, or messing with the yaw, which is the rotation, like just copying the yaw out and then not having any roll and not having any pitch. That's pretty common too. So, but this orange thing here, that's a 4x4 matrix. Kind of. You don't see it that way, but that's basically what it was. That's what we did today. Okay. Yep. So that's our class for today. And like I said, it's not the world's most exciting thing, but honestly, linear algebra is really important to know. And it's just, it's one of those things not taught in a lot of game development courses for I don't know what reason. Like, I don't know how you can get by having a 4-year game dev program and not teach this. Professor, what does this orange thing mean? I'll tell you when you're older. You're too young to know this right now. Go to grad school. I don't know. Like, it doesn't make sense to me. Like, how do you do games without vector math? How do you? I don't know. It just doesn't compute. So, Professor, what's this yellow thing here? What's a forward vector? Like. Okay, so not save any of this, and that's our class. So your job right now is to start working on your mod and your project. Okay, I'm gonna put up a little quiz. We're gonna be doing kind of little quizzes here and there. You've kind of got all the information now for the class. Class is basically, you got pretty much everything. I'm going to have to go through my notes, make sure I didn't forget something, but I think you basically got the whole class. And so you've now got 5 weeks to work on 2 projects. Don't wait until the last minute, because the projects take a long time. And if you wait till finals week, you are going to die because you're going to have finals and working on your mod and your project at the same time. So what I'm going to do is I'm going to set a deadline of like a month for the mod, and I'll do a presentation then. And in reality, you can turn it in, before the Thursday of finals week, and I'll take it. But it's one of those things, like if you don't have time management, I'm just going to create some fake deadlines for you all, and that might kind of give you a little bit of an incentive to get it done, because we'll do a presentation, and if you're not ready for the presentation, you'll be embarrassed. And so I'll give you guys probably about a month to work on the mod, but really it's till the end of the semester, which is in 5 weeks, I think. So, yep. And so tomorrow at 4 o'clock, there's a Minecraft modding thing. So if you're going to be modding Minecraft, come to the talk. It's probably going to be useful. Betancourt did a great job last semester. All right, so that's it for IS50A, IS50B. I am going to just take a quick break, and I will be back after these messages.